Hi, so in this video I want to discuss the formal definition of a limit as it is presented in your book using the epsilon and deltas, and then give you a graph to kind of show you what that looks like. So let's first talk about the definition of a limit. So suppose f of x is a function. Then we say the limit as x approaches c of f of x equals L. So this is right, the limit as x approaches c of f of x is L, means that for all epsilon greater than 0, there exists a delta greater than 0 such that all of your x values are within c minus delta c union c plus delta, such that, if your x values are in this punctured interval, then your function must be contained within this interval of L minus epsilon, L plus epsilon. So we have, for any epsilon that we choose, there must be a delta greater than 0 such that all your x values are on this punctured delta interval around c, and your function values must be within this epsilon interval around the limit value. So let's look at a picture of this. So here's my x's, this will be my y values. So say we have a function does something like that, and this can be, say perhaps we have a hole here and our x value is c, and this occurs at the y value of L. Then what this definition says is no matter what epsilon I choose, I'm going to be able to go a little bit above L, we'll say L plus epsilon, and a little bit below L, L minus epsilon, and create this epsilon band around that value. And there will then correspond some delta greater than 0 that's a little bit above c, we'll call that c plus delta, and a little bit below c, c minus delta, such that you create a delta band around the point 2, and all of your function values are within this band for any, or for whatever delta you choose, because there must exist that given this epsilon band. And so you can see that all the functions get contained within this little rectangle that we have created given some epsilon. So that is the formal definition of a limit using the epsilon deltas. Now another way we can write this is to exclude this notation and change it to an absolute value inequality notation. So let's look at that. So here is the same definition, just written using the absolute value inequality notation to say this exact same picture. And the reason I would want to talk about what this means that we are a punctured interval centered at C with a radius of delta. So if I was to draw the picture corresponding to this, it would look like on the x-axis some C, and we can't be C, so it has to be a hole at C, and I'm going to be delta above, and this is going to be C plus delta, and I'm going to be delta below, this is going to be C minus delta, so that this delta distance is the same above and below C. Now, the trick is, where does this 0 come from and why do we have to have it? Well, this 0 tells you that your distance cannot be 0. We don't have this equal to. If your distance can't be 0, that means you cannot be the center value. As we're with this, there is no greater than 0. So this means that you actually could have the value of L included in there. It's just the C value that is the issue. So when you think about that, what this is meaning is that we are restricting the domain. And even a restriction in the domain does not necessarily mean that we have to restrict the range, because this graph could take a turn and come back down, and so we would have the function defined over here for a new value, but it is not defined here. So I don't want to restrict the range of the function, only the domain or the particular discontinuity, that's a word we'll learn a little later, where the particular discontinuity is coming into play. So again, I have to puncture out the interval around C, but I don't have to puncture out the interval around the limit value. So this is the formal definition of a limit. I just want to do one example where we actually write a limit expression in its formal definition using this absolute value inequality notation. So we have this limit expression. It says the limit as x approaches pi over 4 of tangent is 1. And we would think that to be true. If we look at the graph of tangent, as it gets closer and closer to pi over 4, we get 1. Or if we think about tangent, it has no breaks. It only has...
I definitely meant to say not breaks, but holes. So tangent definitely has breaks. I'm going to say that it has those vertical asymptotes, but tangent does not have any holes, which is what I was trying to say.
It only has vertical asymptotes, and it doesn't have vertical asymptote at pi over 4. It only has vertical asymptotes at pi over 2 and multiples thereof, or also 3 pi over 2, which is a multiple of pi over 2. But anyway, so it would seem like the function value should just be whatever we plug in and get 1. So how would we write this in the definition? So our answer would be, it says, for all epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than the absolute value of x minus the c value, in this case which is pi over 4, is less than my delta, then the absolute value of tangent of x minus 1 is less than epsilon. So now notice this time I'm replacing f of x, my function, with the function from the actual problem. Just to highlight, this is my c value. That's what's getting replaced in the definition. Also, the tangent is getting replaced with f of x. And the actual limit value, which we specify to be L, is getting replaced right there with 1. So those are the only three things that get changed in the definition of the limit.